In this lesson, we're going to introduce some of the main concepts involved in game theory, including the idea of a zero-sum game between two players, a payoff matrix, and a play-safe strategy. So we're going to start by considering a series of 3 games, each between 2 players. You might like to play this game with someone else, or you might like to just consider what would happen in each situation. So each game will have 2 players. One will be player A, one will be player B. We're going to imagine that each player starts with 20 points. And then in each game, each round, the players will decide which strategy they're going to play. They're going to write down their strategy choice on a whiteboard and not show the other person. Then at the same time, the players are going to reveal their choices, and then the number of points will be added or deducted depending on what the outcome is. This will then continue until one player reaches 0, and then the player with the most points at the end will win. So in game 1, player A has 2 choices, option 1 or option 2, and player B also has 2 choices, option 1 or option 2. The number of points that are either won or lost in each scenario is shown below. So pause the slide and consider which strategy each player should take. So having played this game a few times, you may notice that there is no benefit for player A to ever play option 2, because when they play option 2, they will always lose, regardless of what B chooses. So player A is always going to choose strategy 1 if they want to win. And because of that, player B will also be better off playing option 1, because if they choose option 2, they will always lose 2 points. So the overall effect of this game, if this happens every time, is that both players will score 0 each time. There'll be no overall winner. It will just continue in this manner with each player scoring 0. So game 2 has more options. So player A has options 1, 2 or 3, and player B has options 1, 2 or 3. So this time there are 9 different outcomes. Again, pause the slide and consider for each player which would be the best strategy to play. So having played game 2, you may have realised that player B, if they play option 1, they will always win, regardless of what A chooses. So it's sensible for player B to always choose option 1. If this happens, then A is always going to choose option 1 as well, because although they will still lose a point in this situation, it minimises their loss, because if they played option 2 or 3, they would lose more points. So the overall effect of this is that if this continues to happen each time, B choosing option 1, A choosing option 1, each time B will win 1 point and A will lose 1 point. Finally, game 3. Again, you may want to pause the slide and either consider or actually play the game. So in game 3, there isn't an obvious choice as there was in game 1 or 2. There isn't a particular choice that either player could choose that would always ensure that they would minimise their loss. Sometimes there will always be a risk of losing more. So what will probably end up happening here is that each player will play a mixture of different choices randomly. So they will not always choose the same option. Sometimes they will choose different options. This is called a mixed strategy, and we will be looking at the mathematical ideas behind this in this topic. So this topic of game theory is going to allow us to formalise some of the ideas that we have introduced by playing each of these games. Game theory doesn't always allow a player to win a game. However, it does help them to choose strategies that will minimise their risk of losing, or to minimise the amount that they might lose each time. So there are a lot of real-world applications to game theory, for example in business, where there might be several different strategies and different outcomes based on both the choices of a business and also the choices of a rival business. In game theory, a zero-sum game is one where the amount that one player wins each round is equal to the amount that the other player loses. So for example, if one player wins, they may win 2, the other person will gain -2. So together, the gains and the losses in each round will always add to 0. A payoff matrix is used to show the results where there are several different options for each player. Here's an example of a payoff matrix. So for example, player A may have 2 options, strategy 1 and strategy 2. Player B may have 3 options, so 1, 2 and 3. Notice that the number of options available to each player doesn't need to be the same. The elements in the payoff matrix always represent what the person on the left-hand side, in this case player A, will win. And as a result, that also represents what player B will lose. So for example, the 1, 1 in the top left, the number 3 says that if those options are picked, then player A will win 3 points and player B will lose 3 points. If a number is negative, that represents player A losing that amount. So therefore, player B will be winning. So in this -1 here, A is losing 1 point, so B would win 1 point. Payoff matrices always represent the winnings for the player on the left-hand side. So we're now going to consider the idea of playing safe. In other words, trying to minimise the amount that you might lose. So if we're given this payoff matrix here, showing the potential winnings for player A, if player A were to play strategy 1, what is the biggest potential amount that they could lose? Well, if A is playing strategy 1, then B could either play strategy 1, in which case player A would win 1, or if B chose strategy 2, then A would win 2. The big potential loss is actually that A will win 1. What if A was to play strategy 2 instead? So this time, if A was to play strategy 2, then if B chooses strategy 1, then we can see that A would actually lose 2. Or if B were to play strategy 2, then A would lose 6. So the worst outcome in this situation is losing 6. So the 2 numbers in the column on the far right show us the biggest potential loss. In other words, the minimum value in each row. Now let's consider for player B. Remember that the values in the table represent losses for player B. So if player B were to choose strategy 1, then depending on what A chose, they would either lose 1 or the -2 actually represents that they would win 2. So the worst case scenario for B, if they choose option 1, is that they would lose 1. If player B were to choose strategy 2, then again the worst case scenario, remembering that negative numbers represent wins for player B, then the worst case scenario is this loss of 2 here. So what we're doing here is we're taking the maximum value in each column, because that represents the worst case scenario for player B. A play safe strategy involves taking the worst case scenario for each player and choosing the best of these. So in this situation, first of all, we're going to consider the worst case scenarios for A under either strategy 1 or strategy 2. They are the row minima, so the minimum values in each row represent the worst case scenario for player A. We are then going to choose the best of these outcomes because that is the safest strategy for player A to choose. In this case, the largest of the 2 numbers, 1 and -6, is 1. So this is sometimes known as the max of the row minima, or max row min. This is saying consider the worst case scenarios for player A and then choose the best out of the worst case scenarios. We're now going to consider the maximum in each column. Remember that the maximum in each column represents the worst case scenario for player B, because large numbers mean that they are losing a lot. So the column maxima, we want to minimise this risk, so we are going to choose the smallest of the column maximum values. In this case, the smallest of 1 and 2 is 1. This is sometimes known as the minimum of the column maxima, or min-col-max. A game has a stable solution if the play safe strategy for player A is equal to the play safe strategy for player B. So as we can see here, the maximum of the row minima, the max row min, is equal to the minimum of the column maxima, the min-col-max. So we've ended up with the number 1 for both. So this represents a stable solution. What this means is there is no incentive for either player A or player B to play any other strategy apart from a play safe strategy. It's in both of their best interests to play safe. In this case, we do have a stable solution, and the value that we get here, in this case 1, is called the value of the game. So the value of this game is 1. If both players were to play their play safe strategy, then the value of the game is what you would expect player A to gain each time. So each time this game is played, if both players play safe, then we would expect A to win 1 each round. The position that this occurs in the matrix, in this case with both players playing option 1, is called the saddle point. So the saddle point is shown there by a red square. So for this zero-sum game between player A and player B, we're going to show that the game has a stable solution. We're going to determine the value of the game and the location of the saddle point. The first step is to consider the minimum value on each row, so the row min. This is the worst case scenario for A in each case. So if A chose option 1, the worst case scenario, or the minimum value, is that they would get -1, they would lose a point. If A were to choose option 2, then the worst case scenario, the minimum, will be -6. And if A were to choose option 3, then the minimum value, the worst case scenario, would be option 1. So the maximum of those 3 numbers is 1. So in other words, A's play safe strategy would be to play option 3, because the worst case scenario for them would be that they would win 1 point. Now for B, we're going to consider the maximum value in each column, remembering that large numbers are bad for B because they are losing. So in strategy 1, the maximum in the first column is 3, so that would be B losing 3. In option 2, the maximum number in that column is 1, which represents B losing 1. And in column 3, the maximum is 3. So remembering that we want to minimise the risk, and remembering that small numbers are good for player B, we now need to find the minimum of the column maxima, and the min-col-max is also 1. So the fact that we've got the same number for both tells us that we have a stable solution. So we would write stable solution as max row minima equals min-col-maxima. The value of the game is therefore 1. This means that each time the game is played, if both players play safe, then A will win 1. The saddle point is shown there. It is with player A choosing strategy 3 and player B choosing strategy 2. Next, we're going to determine whether this game has a stable solution. So we're going to do this by finding the row minima. The row minima for the first row is -1, and for the second row is -3. So they are the worst case scenarios for player A. The maximum of these is -1. I'm now going to find the column maxima, so the worst case scenarios for player B. The maximum in column 1 is 2, the maximum in column 2 is 1. We now want the minimum of these. The minimum of the column maxima is 1, and because these values are not equal, we can conclude that there is no stable solution for this game. Now pause the slide, and for each of the following games, determine whether there is a stable solution. If there is, state the value of the game and show the location of the saddle point. So the first game, we have the row minima as shown, and the maximum of those is -3. We have the column maxima as shown, and the minimum, there are 2 minimums here, so we can circle both 0. However, the numbers are not the same. Max, row, min does not equal min, core, max, so therefore we can say that there is no stable solution. For the second game, the row minima as shown here, and the maximum value of that is -1. The column maxima as shown below, and the minimum of that is also -1. So because we have the same number, max, row, min equals min, core, max, we can say there is a stable solution. The value of the game is -1, and the saddle point is shown in the red square. For game 3, we have the row minima as shown, and the maximum value is -1, and the column maxima shown here, and the minimum value is -1. Again, we've got max, row, min equals min, core, max, so there is a stable solution. The value is -1, and the saddle point is shown in the middle. And finally, for the fourth game, the row minima are shown here. There are 2 maximums there, so we can circle both. The column maxima are shown at the bottom. Again, there are 2 minimum values there. So there is a stable solution, v equals 0, the value of the game is 0, and there are actually 4 saddle points here because each player has 2 play safe strategies. Now complete exercise 6.1 on page 93.